Yes,
Sure.
Yes, go ahead. Go ahead.
So I'd like to ask a question about this, maybe a little bit of detail about the machine learning part. So when you are trying to generate new structures for the metasurface, so you have using, I did not quite remember, you use a two-dimensional input for the representation of the geometry, or using one-dimensional representation of the geometries. Currently, actually, I have doing something just using one-dimensional input. I think for two-dimensional input, there are advantages, like they can more represent the collections between the different part of the images. But I have not tried that, so I'd like to maybe know some experience. So which one do you think is better, or?
Well, I think it would depend, yeah, on the problem that you're attacking. Like in our case, it is a two-dimensional distribution. So you have a two-dimensional distribution of your initial distribution, right? So, and this is just a function that you randomly select and start with. So it's 1 for titanium nitride and 0 for air.
Yes.
Right? So that's a distribution that you have. That's your function. Now, for our system, what's important is to impose some restrictions. So obviously, what you have to think about when doing such optimization and generating your training set is that you have to produce a structure which can be fabricated, right? So so the features of your function should not be smaller than, let's say, 40 nanometers.
Yes.
And you also try to see whether it's robust enough. So you erode and dilate it a little bit to see that it's stable. Now, what you say is also interesting, because what I showed and talked about very briefly for the QUBO system, like, for example, if you want to solve similar constraint problem on a D-wave machine, then you cannot work with a two-dimensional function, right? What you need is a binary vectors. So how you map the original distribution function into binary vectors.
Well, I just maybe mean a very naive mapping, just by flatten the two-dimensional vectors to a one-dimensional vectors, just flatten it, right? You can, so that's a very naive trade-off.
Yeah, but I think, well, you should be able to, you'll get greater flexibility and access to like more designs, obviously in a two-dimensional case. That's one thing. What you can do if you'd like to like play around more with that, you should actually work in a compressed space. So you can do more things in the latent space than with a physical system. So instead of playing with your original function, like you can actually do the things in the compressed space of your variational or adversarial autoencoder, and then you can do more things. So I will be happy to talk more with you about this, or you can just shoot me an email, and I can also connect you with people doing that, and then you can check whether there are some things that you could apply and cross-learn.
Okay, thanks.
Thank you. Do we have more questions? I have one that is written in the chat, but actually privately to me. I'm just going to read the question. Are you developing your own machine learning codes or using ones already available? In any case, what is the best machine learning paradigm suited for photonics and acoustics metamaterials?
To start with, we have used just commercially available techniques. So GAN, VAE, and AE, these are all standard techniques. Now, where your like input is critical, and where like photonic part starts is in creating your training set, right? So the training set should be large. So now one problem in photonics and why machine learning is not widely used in photonics is that in order to train any network, you need at least 10,000 items in your training set. Now, generating 10,000 designs like they are optimized in a training set is very time consuming. So that has been limiting this area. Now, what you can do and what we are doing is you can design your training set and optimize it for maybe 200 designs. But then you should use physics, or you should use the information from physics that you know of this matter surface to expand it. Now, what kind of physical mechanisms can help you? Well, you can use a rotational, translational symmetry. So you can use symmetries to help you to extend the training set. Now, that's exactly what we do. So we generate to 100, but then you use the symmetry properties and translation and other things to generate more. So that has been critical for us. But moreover, when your GAN or other network generate the first set of optimized designs, you can feed them back and use into the training set. So it's like a feedback loop. You generate the first batch, you check them with the direct optimization, and then you feed them and expand your training set. Now, which one would be the best? There is no answer, but you should look into descriptions. So for example, GANs are known for being largely limited to the training set. So essentially, GAN will give you designs that are very close to the training set. And in many cases, you want, as in our case, we want global solution. So we are not satisfied with that. We don't want something which looks very similar to the training set, because it means that it will have very similar efficiency. We want outliers, something which is, outside the training set, something that you have not thought about yourself or haven't seen with direct optimization. In this case, adversarial autoencoders would be better. So they have because again, they don't work with the geometrical representation, they work with a compressed representation. And the compressed representation, you can yourself then inject a little bit of physics or restriction that you have in mind. But frankly, I think that at this point we have to work with computer scientists who will be developing techniques specifically for the problems, let's say, in matter surfaces. So there should be some kind of physics-informed machine learning techniques. And that can only be achieved when photonic scientists are working with computer scientists. And that's what we are trying to achieve. We are teaming up with computer scientists, and we are hopeful that we'll be able to develop more physics-informed systems. I don't think that there is a best machine learning approach for matter surfaces. It's largely depend on what you have in mind. As I said, even for the problem that I described, and we are still looking for, and D-Wave is our last trial or last experiments that shows, high efficiency. But definitely for it's only for the distribution of the top layer. So if you think that now I want to change my mirror thickness as well, so how about I change all the thicknesses and as parameters as well? And as I showed, titanium nitride is tailorable, so its dielectric permittivity is also a parameter. So what if I want to include all of it? And that would be hard, like then you would need different techniques and maybe some kind of hierarchical machine learning. We are thinking about it, but that would be next step, and that's what we will have to do if we really want to achieve globally optimized matter surfaces. It has to be both topology or shape, has to be constituting materials, and it has to be architecture overall.
I hope that this has answered the question, the first question asked in the chat. Just to continue on that point, I was wondering, I mean, here you said you introduced the symmetry, the group of symmetry. For example, you say, okay, I have some rotational, some translational parameter that I can just work on one unit cell. I was wondering from the physical point of view, do you implement any bounds in a way that that, let's say, in the two-dimensional space, you say, okay, I'm using these materials, and from some bounds, I can know, for example, that the conductivity will not be higher depending on how many other material I can mix. And this bound aspect is very important because when you interpolate inside of your algorithm, I think it does not matter too much. But if you want to extrapolate, you have to know until which point you can extrapolate from the bounds. Otherwise, you will somehow have to shoot in a direction, but you don't know how far you can go.
Well, that's absolutely true. Yeah, I mean, obviously there should be boundaries. And well, for example, if you are thinking about introducing like a dielectric permittivity as a parameter, right? Obviously, it should not be like free fall, right? So, most likely you have to start slow, and you should like maybe select certain points and maybe select, I don't know, several dielectric permittivities, and then search for those fixed values and see where everything is going and whether there is a trend that you can see. People do ask about like unstable solution, because that's obviously another boundary, right? You don't want to find a solution that would be like a singularity, and that's why post-processing for the designs generated by machine learning, you still would like to do maybe just a couple of iteration of direct topology optimization, because you want to make sure that this is a robust and stable design. So there are many constraints, and altogether we can say that this is something that should be physics informed.
Thanks. Do we have some more questions?
So when you're talking about this GAN network, could you please go to the slide that's showing the GAN network? So the discriminator is trained to detect whether the input is from the image or from the fake data.
No, it's essentially, let me see. So everything is generated by the generator, but the discriminator, I'm trying to see if I, topology. Yeah.
Yeah,
fake in this, right. So real and fake in this way, it's more whether that's something that would give you the intensity that you want, right? So your training set is already pre-selected to
yes.
to be highly efficient. So now that's what your generator is trying to do. So it's trying to imitate what's here and pass it through. So what happens here is, let's say your generator generates something which looks like a training set, and discriminator would compare those and say, hey, it's fake, it will block it, right? But the next time it will adjust, and then it will generate something that now looks very similar, has some features that discriminator would say, hey, that's real. And that's what we will, you know, consider as being a high efficiency or potentially high efficiency as well. So that's like in very simple terms.
Yeah, I understand. So it is competition between this generator and this discriminator.
Yeah.
So my my question is, is it possible that to replace this discriminator by some, let's say, some mathematically constrained conditions? Because this discriminator, its main goal is to determine whether the output image from this generator is more or less physically reasonable, or let's say capable of fabrication.
No. Discriminator is not doing that. Discriminator and generator, they do not care about how fabricatable your design is. So all the boundaries are in your training set. So your training set is made in such a way that these designs are robust and these designs do not contain features less than 40 nanometers, because that's what we use in direct optimization. Now, when GAN generates your systems, they can still have this, you know, smaller things in them that you have to get rid of. So and that's so that's why for any generated set, you would need to run this few iterations of design optimization, like with a conventional one. But then it's not very time consuming, right? Because you don't start from random guess. You start from the set, which is generated by GAN, which GAN produced as being efficient. And then you just, here you check that it actually physically possible. So your physically possible things and boundaries so far are outside the GAN. So very often how I vision it, and that's my understanding because I am actually a material scientist almost and not a machine learning person, but how I see it is mostly like people call it as a black box, machine learning black box. You feed something in and you get something out, right? So whatever we are injecting from our knowledge of physics, with those boundaries and restrictions, actually before and after. The physics is sitting in the training set and in the post-processing, like optimization. Now, as I was asked about best approaches in the future for Metasurface designs, we have to inject the physics inside the black box, inside the machine learning. But I don't know how to do that because I don't develop machine learning algorithms, and I never will. So it has to be people that are working with ML techniques that could work with us.
So for your generators, your input is just a random seed, right? For this generator, so the previous slide.
Yes.
So it's just a random number.
Yeah, but it's still but the training set is what have all this.
Yeah, the training set already contains some information that you aimed at to be optimal.
Yes.
Well, yeah, maybe my just a very simple replacement is by, when you mentioned about there are small features that are, let's say, less than 40 nanometers by this generated images. So maybe just simply replace this constraint, replace this discriminator by this simple constraint. But that just maybe seems to be too few constraint instead of by using this discriminator.
Yeah. As I said, generator and discriminator are part of this black box that does the machine learning part. They don't care about your restrictions. You have to do it afterwards.
And for the performance of these generators, do you have estimations how
Well,
Also, how many
I
samples the produced image are optimal?
Yeah, I didn't show that, but definitely GAN designs, they will give you higher efficiency than a training set, a little bit. So not, as high as the AAE later, but maybe 95% instead of 92 as the highest efficiency design. Yes.
Okay, thanks.
Very much. Do we have a more question?
I have one more question.
Yes, please. Go ahead.
Sorry, I don't have the camera. Actually, the latent space in the variational encoder is the normal distribution, right? While the AE you mentioned before means that we can define the distribution we like, such as the uniform distribution in latent space, right? Well, generally, from my knowledge, I think the distribution in latent space is mainly said to be the normal distribution. So I'm so confused that will the distribution in latent space will affect the training process, or will affect the representations of latent variables from the training?
Well, I think that's exactly the point of further investigations in this area. That's what I call like interjecting into the black box. Definitely this would influence the whole operation of your machine learning system. And you can indeed force your latent space to predefine model distribution, which would be different from the normal one. That's the point, and that's where like interesting things could happen.
Actually, the autoencoder is aimed to extract and find the structural parameters in the system. So, I think it should not be a black box. So, I
agree. I'm saying it's black box for like researchers that are using it, and we have to come like from material side and device implementation. Yeah, you're right. Yeah, right. We have to work across the fields for sure to, and that's why we need like more people. Like we are constantly looking for like postdocs and for students that would be able to apply and more importantly develop machine learning techniques for photonic problems. And I actually will use this opportunity to say that we are looking for a postdoc in the area of quantum and machine learning very desperately. So please email me after the talk, okay? I tried to post it on the Twitter and other social media, but I got some weird applications. But I'm using this opportunity to call for people who are able to do machine learning and interested in quantum applications. Please reach out to me. Thank you for all your questions.
Actually, I think this is the advantage of autoencoder, because we can make use of the latent variables to represent the structure, the real physical parameters in the
absolutely.
In the systems.
You are absolutely right. Absolutely right. That's where everything should be going. Yes.
Okay. Thank you very much.
Thank you for the question. Do we have any other question? I don't see in the chat. If anyone has a question, you can just come up and ask it directly.
You are always welcome to send me an email. We are a very active group of people, and we are happy to discuss both our and your work. Thank you for listening.
Thank you very much, Professor Boltasseva. It was a very nice talk.
Thank you.
Yeah, so please feel free to contact her directly if you have any questions.
Lovely talk.
Thank you.
Thank
you.
you all very much. Thank you for inviting.
Really exciting topic. So we want to learn more definitely on this kind of exciting machine learning topic.
Yes, the same here. We are also
yeah.
still learning.
Nice.
Thank you all.
Really exciting also for the possibilities it opens in acoustics and elastic metamaterials. I think it's
I believe it should be we should implement it everywhere. As soon as we designing something, we are limited by a priori knowledge and our input, right? You want to get out of this region, and you have to use machine learning. And by now we have enough expertise from other fields to teach us how to create enough data set, because data set is all the problem why in photonics we have not used it for a long time, because we didn't have the training sets that are big enough, and that was a very simple reason. No one is doing the measurements, or no one is running simulations for 10,000 times, right? Because it will take forever. And that was limiting us. But again, we can use physics and all the different things to produce a large training sets now.
Right. I hope we can meet in person, perhaps in New York at MetaMaterials.